Hello and welcome back to Business Analytics. My name is Hari Rajagopalan and I'm your instructor for this lecture. So now that we are firmly in predictive analytics, we are talking about regression, which is the foundation of any predictive analytics. And in this lecture, we are looking at simple regression. Now remember, in the last lecture, which you should have looked at, you went through how you can calculate simple regression manually with formulas and how to do those same formulas in Excel. I went through very quickly, and so now we're going to talk about the least square method and how we're going to use solver in Excel to do this. So we talked about simple regression being one independent variable, one dependent variable, both being continuous. We generate equation of a straight line. And we actually use the least square method to minimize the errors. So let's talk about what this least square method is. Now, for this, you either use solver, and this is the interface that Excel gives for solver. Those of you who are using Mac might have a different solver, or if you have downloaded and installed Analytics Solver, this would be the interface you're going to see. And I'm going to do both in Excel. So and essentially what we're talking about here is the objective, which is to minimize the squared error. And the changing cells are the intercept and the slope. And let's go to Excel and figure out how to do this, this in Excel. So before we start this, let's look at whether you're going to use the Analytics Solver, which I've asked all of you to register and download for this class, or are you going to use the solver which comes in Excel? So if you click data and you don't see solver here, you should go to File, Options, Add-ins, click Go, and make sure the solver add-in is selected. And when you click OK, you should see solver appear here. So you can either use Analytics Solver or you can use this. If you're using a Mac, there's a similar method. You can probably YouTube for it. So essentially what we're saying is predicted sales is going to be intercept plus slope multiplied by your independent variable, which is student population. And you can copy this and paste formula all the way down here, right? So let's go ahead and make sure it's a number and that it has a comma, right? So squared error would be your actual sales minus your predicted sales, or the other way around. Whole squared, predicted minus actual or actual minus predicted. It doesn't matter because you're squaring it anyway. And there you go. And let's make sure our formatting is okay, because formatting makes it easy to look. So let's look at the average squared error. Now that we got the squared error, let's take the average squared error. And then let's look at the root of the average squared error. So we take the square root of it. Now you want to be careful that this is not mean squared error. This is definitely not mean squared error, because mean squared error would actually not take the average of it. It would take the sum of all this, which is sum of squared error, divided by 10 minus 2, because we already have the intercept and slope calculated from here. All right, so don't get confused with the mean squared error and the average squared error, okay? Average squared error, assuming this is a population value. All right, so now we're going to look at the intercept and slope. And we want a value of intercept and slope such that this average squared error is the minimum. And before we do that, let's go ahead and plot this data. So I'm going to go ahead and plot this data. Here is my actual sales. And then I'm going to add the prediction. And let's let the prediction be, let's go ahead and put it as a line. It's a straight line. So here is the predicted value. So I'm going, I would rather have the predicted value. So let's go ahead and put a 50 here, and you can see that it actually moves up. And then let's add a slope to it. 2, well, maybe 3, maybe 5, right? That looks better. Let's go to 52, move it up, maybe 60. That looks better, right? And we know the answer because we already calculated it. But Solver can do it for you. So go to Data, Solver, and we are going to minimize, make sure you understand that minimize is selected, average squared error, by changing the intercept and slope, right? And you go ahead and click Solve, and you automatically get the values which will minimize the average squared error. And you notice that it goes right up here. If you're going to use this solver, you would actually go here and say objective. Again, double click this objective here, minimize D12, E12. Your changing cells are these two, and then you can click solve. All right. So this is essentially what we're doing. We're minimizing this by changing the values of this. Any other value of intercept and slope will give you a higher value. All right. And what it does is it tries to make these blue points and these orange points as close to each other as possible. Okay. And that's basically your least square method. So we're back in PowerPoint right now. Let's go to the next slide. So the other way to run your regression, and this is how you're going to run your regression throughout this class, is to use the data analysis regression. And this is the interface you're going to get when you get this data analysis. Your input Y range is going to be your Y variables. Your input X range is going to be X variables. If you have labels, that is, if the first row contains headings, you're going to check this labels. We are not going to look at this constant as 0 right now. If your confidence level, you can put it 99%, depending on what your alpha is. Alpha is 5%, confidence level is 95%. If alpha is 1%, your confidence level is 99%. You can get it in a new output range. You can go to a new worksheet or a new workbook. And here are some values which will actually do the calculations for you. Residuals, standardized residuals. These will actually calculate the error. Actual values minus predicted values will be automatically calculated. It'll also show you some residual plots and line fit plots and normality plots. When we look at the assumptions of regression, these will come into play. And it would be important. So here are, and as I talked about, independent variable, dependent variable, other outputs. So let's go to Excel again and run this regression so we can look at the output. So here's the data set again. And if you go to data analysis, and then you've seen this before, if you go to regression, actual sales is your dependent variable. That's your Y range. X range is your independent variable. Labels, confidence level. We're going to put this in this output sheet, and we are basically generating all the possible reports that we can. And here we go. Now my suggestion is that you automatically, first thing you do is to go ahead and format. A lot of you make mistakes because you don't format your data. Like for example, this significance F, a lot of you have trouble with this E minus 0.5. So just go ahead and format it because that will give you a better understanding of what that number is. And similarly here, these are numbers. These are all confidence intervals, so you don't have to calculate the confidence interval for the slopes. It's given to you, and here is your values. And you'll notice that for simple regression, t-test p-value is same as this. And you're also getting the residual outputs. you have predicted actual sales, residuals, and then your standardized residuals, kind of looking at it. So this predicted actual sales and the residuals are actually your errors. So you can go ahead and plug it in here. So you don't have to literally calculate your predicted actual sales. It's actually given to you, and then the difference between the two is given here. So you don't have to do it manually. And I'm going to talk about each one. And here is the probability output. Here are some charts. You have residual plots, line fit plot, and normality plot. We're going back into PowerPoint to talk about these plots. So back into PowerPoint, let's go back and look at the output. So we have summary point. Multiple R is your correlation coefficient, which is the square root of your R squared. Your adjusted R squared is not something you're going to use for simple regression, but you're going to use it for when you do multiple regression. When you do multiple regression, you don't use R squared anymore. You're going to use adjusted R squared. And multiple regression is when you have more than one independent variable. Your standard error, this is your square root of your mean squared error is given here, and number of observations. You also get an ANOVA table where you have your mean squared to regression. Mean squared residual is your mean squared error. And then the ratio gives you your F-test. And of course, here's your p-value for the F-test. This is the sum of squared error. Remember, sum of squared regression, sum of squared error. And then here is your sum of squared total. And here are the degrees of freedom. Regression, you have only one independent variable, so degree of freedom is 1. For residual or error, it's sample size minus 2. And then you add them. That's the degrees of freedom for sum of squared total. For the intercept and slope, here are the values for intercept and slope. Here are the standard errors for the intercept and the standard error for the slope. Remember, you calculated manually the standard error for the slope. Here are the t statistics for the intercept and slope. Their p-values both are highly significant. And here are your confidence interval, 95% confidence interval values for the intercept and slope. And your residual output, here is the predicted value. So this is the values on the line. Here are the residuals, and now we are standardizing those residuals. And here is the probability output, at 5 percentile, at 15 percentile. I'm going to go over each of these outputs and talk a little bit more out of it. So your actual sales, the 5th percentile is about 58 and so on. So let's look at the regression Excel plot. The first one is the plot for the residuals. So the residuals are plotted based on the student and plotted with respect to your independent variable. And you want it to be random. That is a little bit up, a little bit down. You don't want a pattern. And it looks like this. That's the first assumption in regression, and it looks like it's okay. This here is the line fit plot, which is the same as this. Your predicted sales comes here, and here's your actual sales. And you can see that there's a reason why this residual is both up and down, and there's no pattern here because this is right in the middle. And then finally, you have the normal probability plot. If your data is normally distributed or your errors are normally distributed, this should be approximately a straight line. So if it's a straight line, and we'll talk more in detail about these assumptions. So your multiple R or Pearson correlation should be, when we talked about it, should be between -1, 0 and +1, and it's 95.01% or 0.95, which is pretty close to 100%, and so it's a positive relationship. R squared, we can explain about 90.27% of the change in quarterly sales due to the change in the number of students. Adjusted R squared, if you have a lot more than one independent variable, R squared just increases because you have more than one independent variable, and therefore you're using adjusted R squared to manage that. Standard error measures the precision of the model. It provides the absolute measure of the typical distance that data points fall from the regression line. Like the distance from the, on average, how far is the blue dot from the predicted value, right? So on average, your sales prediction for pizza is off by 13,830, right? 13.38. And the difference between R squared and standard error is R squared is a relative measure, right? Whereas standard error is an absolute measure. So R squared is like saying my salary increases by 50%. And that is that 50% from 1,000 to 15,000, sorry, 1,000 to 1,500, or from 10,000 to 15,000. Here it's increasing by 1,500. Here it's increasing by 5,000. Both are 50% increase. So you need to know how much actually. So standard error with R squared helps when you look at the values. So you need to know how much the increase was, and the relative measure is not going to give you that. So let's look at regression. The regression, we look at degrees of freedom is the number of independent variables. I talked about the sum of squared regression, mean squared regression. Your residual looked at the degrees of freedom, which is sample size minus 2. You had sum of squared error and mean squared error. And then you have your F value, and your intercept and slope data was also given. And we talked about this ANOVA table. This is the row gives you the regression details. This gives you the residuals. This gives you the total. And then with your intercept and slope, you get all the information you need. So let's get into the intercept and slope. So your predicted sales, the model essentially is predicted sales is equal to 60 plus 5 multiplied by student population. So if you're looking at 5,000 students, your predicted sales comes to 85, which gives you 85,000. Slope says for every 1% increase student population, predicted sales increases by $5. And the slope can be positive or negative. If it starts decreasing, then it'll be negative. Intercept essentially means that student population is 0. Your predicted sales would be 60,000. Now, how does that make sense? What do you mean if there are no students, my sales would be 60,000? Who's going to buy these pizzas? Maybe there are other customers who are not students. We don't know about that, right? There could be some other demand apart from student population. The standard error of coefficients is the average error of predicted coefficient, and you want this error to be small. Your t-stat and p-value, again, we looked at it. Now, unlike the manual where you had to compare it with alpha by 2, Excel automatically multiplies your p-value. So the data given to you is automatically multiplied by 2, so you just have to compare it with alpha. You should not use alpha by 2 if you're using the table from Excel. Does that make sense? In the manual calculations, because it's a two-tailed test, you actually used alpha by 2. Your F test was compared to alpha, your T test was compared to alpha by 2. But Excel does not give you just the p-value. It gives you a p-value which is actually multiplied by 2, so you have to compare it with alpha. And you can also get the confidence interval for the coefficients, right? So remember, these p-values are actually multiplied by 2, so compare them to alpha. So we talk about calculating the confidence intervals, and I've already showed you how to do that, but in this case, we're going to use the standard error, and I'm going to open up Excel right now so that you can take a look at how it's calculated. To calculate the confidence intervals of the predicted value, or often called the prediction intervals, you have to look at your independent variable, and you've got to take independent variable minus its mean whole squared, right? And you've got to get the sum of squared here. So the standard deviation of the predicted value would be equal to your standard error multiplied by square root of 1 by sample size plus that value, the squared value here, divided by the sum of squared here. And here's the formula. So you get the standard deviation of the predicted value. And then you can use t-score multiplied by the standard deviation of the predicted value multiplied by the standard value to get your confidence interval. Now, when you do multiple regression, it's going to be difficult, more and more difficult to do this. You need to know about matrix multiplication. So when we start looking at multiple regression, we'll start using an approximation of this using standard error, and we'll talk about it when we do multiple regression. So we looked at how to calculate confidence intervals or prediction intervals, and let's look at the plot output. So we have your predicted actual sales, your residuals, and standardized residuals. We talked about that. And here are the residual plots, and you want to make sure that some residuals or the errors are on the negative and some are on the positive, and there is no obvious pattern here. You want to look at the normal probability plot, which is actually based on this here, the actual sales and what percentile they are. This needs to be straight line, then it's normal. There are some other plots, and what do they mean? So we can have, essentially, if you look at this normal probability plot, here is the normal distribution, right? And this gives you the probability, this area gives you the probability, the area of this under this line. And then if you want to kind of look at the cumulative density plot, it looks something like this, right? So because we are actually looking at the cumulative normal density, the plot will be a straight line. So x-axis is transformed so that the cumulative normal density plot will plot in a straight line. Then we use the mean and standard deviation, which are calculated from the data. Data is transformed into standard normal values, where mean is 0 and standard deviation is 1, which means you're looking at z-scores. Then the data points are plotted along a fitted normal line. So if your plotted points don't fit the line well but curve away from it in places, you may not have a normal distribution. So here are some of the other distributions you are looking at. If it goes like this kind of shows a right skew for your distribution. If plotted points appear to bend up to the left, and then similarly here, this kind of pattern shows a left skew. If it like an S-shaped curve, this means that the data has short tails. It has less variance than expected from a normal distribution. And if it's something like this, then it means this is a long tail. That means you have a lot more variance than you expected. Let me talk a little bit about what short tails and long tails mean. When you have a long tail, it means that the probability of getting an extreme value is more probable than if you have a normal distribution. Short tails, the probability of getting an extreme value is less probable, okay? So it's important for you to understand what that is. And finally, you can also calculate the predicted value using the trend function, and I'll show you how to do this in Excel. Also, you can create a trend line using the data set, and I'm going to show you how to do this in Excel. So let's go to Excel before we end this particular session. For the last and final thing I wanted to show you is the trend function. So you can actually use the trend function to get the predicted sales, and the trend function essentially asks you for known y's. So known y's is your actual sales. This entire thing is a y, and you can put F4 to prevent it from changing. Your known x's, these are your x values. You can put that. If there's more than one, you can put it. And then your new x is this, and now constant. In this particular case, you can just omit it because we want them to calculate the constant. So you go there, it will actually calculate it for you. It will give you the actual values using the trend function, okay? The other way of actually getting your data is to do a scatter plot. And once you get a scatter plot right here, you can click on the scatter plot, right click on it, and say add trend line. And when you add your trend line, you can see on the right hand side, it gives you exponential, linear, logarithmic. You can see a whole bunch here. Go ahead and click on linear, and that gives you the regression line. You can say display equation on chart. That gets you your equation. And you can also display your R squared value. So this is pretty quick and easy. You can use it to check your answers and make sure you're getting it correct when you're running the data analysis, because a lot of times students make mistakes with the data analysis. Use this to check whether you're getting it correctly. And with this, we finish this, and we're going to go into next stage is assumptions for regression.